Great. So today's problem is binary tree level order traversal. We've actually done something very similar to this already in a way previous problem, kind of by chance. Yeah, this is day 30. We're officially at 1 month of late code problems, which is really exciting. And yeah, we'll talk about this and then we'll get some context and then we'll go for the solution as usual. So, given a binary tree root, we want to return the level order traversal of it as a nested list, where each sublist contains the values of nodes at a particular level in the tree from left to right. Okay, so in this tree, for example, you can see that we've got, well, you can see it visually here. It's represented in data like this. The output is one big list where each nested list is all of the nodes in a particular level from left to right. So the first list just has one, which is the root. So always going to be one node at the start, assuming that there is actually a node there. And then the next list has 2 and 3. So all of the things from this layer. And then the next list has 4, 5, 6, 7, which is all of the nodes from the next layer. And yeah, pretty straightforward, hopefully. The next example is just this singular node. The output is just a list with 1 because that's the only node. There's nothing in the second layer, so there is no second list. We just return that list that has a list with 1 in it. Okay, and then actually this is the example I was hoping they would provide because I wasn't sure about this. If there is no root provided, then we just return an empty list. And then they clarify for us some constraints here. The number of nodes in the tree is between 0 and 1,000 inclusive, so it could be 0 nodes here, in which case we return an empty list. And the values are between -1,000 and 1,000. That's pretty standard. Again, we're not going to manipulate those, we're just getting the values. So those will be nice and well behaved. So pretty much all the problems we've done in trees so far, the sort of standard solution that we've provided has been a depth-first search. And again, what that means is we're going to go and follow like one path all the way down the tree and then back up and explore the paths that we missed the first time around. This problem is the first one that is pretty definitely meant to be a breadth-first search, which is exactly what we just described. Breadth first means explore all the paths that you can at once and then move on to the next set of paths that you can explore, basically. So this like going level by level is a really, really common pattern that tells us to use breadth first search. It's the one that kind of makes sense for the problem. So I think when we did this last time, when we did breadth first search last time, I think we didn't, why did the tree disappear from this? Oh, jeez, jump scare. I was like, didn't we have an image in here? Okay. So last time we did breadth first search, I think we just talked about the algorithm. Greetings. Oh, great. Great. Anyways, last time we did breadth first search, I think we just talked about the algorithm and we just went for it. Let's do a little bit of diagramming just to get some context on how to do this. So let me grab the, oh, hello. I can't draw circles, you guys. It's kind of a problem. Okay, so let's just draw a small tree and then we'll get going on how to carry out this algorithm. And then I'm going to try it as a depth first search as well. It's definitely not built to be one, but I think we can make it happen. So we'll just try it out because we love to have alternative solutions. Okay, so let's say we had, and I'm going to actually we'll make this a little bit messy. Man, I really can't draw circles. I don't know what's going on here. Okay, so I'm going to do this, and then I'm going to put 6 over here. And then maybe we'll have some weirdness where there's a 7 right here. Okay, so basically what breadth first search asks us to do is determine everything that's in a particular layer, and then use that information to figure out how to handle the next layer. So what I mean by this is, when we start, the first layer is always going to be whatever the root node is, right? And what we need to figure out is what are all of the things in the next layer, right? Well, to do this, what we're going to do is we're going to look through the current list of nodes that we're processing, and we're going to list all of their children. So in this case, the only node we have to process right now is the root node 1, and we'll say, hey, the children of 1 are 2 and 3, right? And now we no longer need 1, we've already processed it. Now what we're telling ourselves is, hey, the next set of things to process are the node 2 and the node 3. Okay, so this time there's multiple nodes, totally fine, same process. We'll go through each of these nodes and figure out, hey, what do we need to do to process the next layer? So for 2, we would say, hey, this means we need to process node 4. For 3, we would say, hey, this means we need to process nodes 5 and 6. This provides us the next layer, right? And then we would say, hey, for 4, 5, and 6, what is the next layer, or what information do we have? Well, 4, there is no next layer, right? So that provides nothing, or it tells us there's nothing left to process on this, or at least coming from these nodes, this node. Same with 5. And then 6 finally says, hey, we need to process node 7. And finally at node 7, we stop and we say, hey, there's nothing left. Hey, thanks for stopping in. This is pretty much the whole problem right here, what I said. So we'll talk about how to do it in code, but it'll be in the recording. So, okay, so how do we know when to stop? It's when we get to a point where the next set of things to process is just totally empty, right? We know that we've reached the end, there's no more nodes, we've hit everything once, and we can stop. Great, hey, that was so kind, thank you. All right, and that is that. Now, in terms of how to handle like switching out the old nodes, the new nodes, when we move from layer to layer, there's actually quite a few ways to handle it. I've historically done this with list slicing. I've done it with, last time we did it with 2 lists, which I thought was a really handy way to do it. Here's the problem is we need to add things on in a particular order because we want to go from left to right. So we need to add things onto the end, and we also need to remove things from the front. And if you remember way back to arrays, one of the problems with that is when you remove things from the front of an array, it's really slow. Everything gets copied over one element at a time. So that's O of n time complexity. So we need some way basically to add things onto the end and remove things from the front. I think there's 2 main ways to handle that. One is to just like kind of chop a whole section at a time. And what I mean by that is like if we had 2 lists, one list is going to be like things to process. And then one list is going to be like the next things to process. Right, so when we start, for example, or let's just kind of go into a random layer of this. When we start, it's like 2, 3 if we're at this layer, right? These are the things we need to process. We produce this new list, 4, 5, 6, or we populate this new list, 4, 5, 6. And then when we want to move on to the next layer, we can just say, hey, let me use a different color. Well, let me think about this. Yeah, we can basically just say in terms of variables, hey, go ahead and just empty out this list, which is O of 1 time, because we're just going to replace it with an empty list. We don't need to copy anything over. And then we're going to say, let's make this the next set of things to process. So instead, if we just move the variables around, this makes this O of n. Let me think, there's probably a better way to diagram this actually. Yeah, let me do this with some arrows. So we always need to keep track of like, what do we need to process? And then what is next to process, right? Okay, so when we need to move on to the next layer, we can say, hey, go ahead and replace next to process, or go ahead and replace to process, make it point at this list instead. In fact, you know what, let me do this by like crossing it out. We'll say, don't make it point here, make it point here instead. Okay, and then for next to process, we'll say, don't make it point here, instead make it point at an empty list. So this old list here basically just gets thrown into the void. We don't need it anymore, right? And we just make these point to new places, these variables. So anyways, that's one strategy to get us that O of 1 time complexity, to like switch the lists. The other way we can do this is if we use what's called a double-ended queue, which in most languages gets abbreviated to DEQ, D-E-Q-U-E. And this is basically like a doubly linked list. It just means we can, it keeps track of things sequentially. We can't really get to, we can't like remove things from the middle quickly, but we can remove things from the front and remove things from the back quickly. There's other differences, to be honest. I am not prepared to speak to them extensively today. We'll probably talk about them later. But yeah, in short, the DEQ is another option for us to do that. It is it's because I hate you. That's exactly correct. Yeah, I just don't, to be honest, I haven't used DEQs a ton in Python. I don't know a ton of details about their like implementation. In short, though, the important thing is when we need to remove from the front and the back, or add and remove from the front or the back, like we need both of those to be easily accessible, the DEQ is a good option. There's probably other things like to account for, but that's the primary strength of the DEQ. Okay, we'll go with this solution for today because I think it's a little bit more explanatory. Like it's a little bit clearer what's happening when we do it manually rather than just letting the DEQ handle it for us. But the DEQ is a good data structure to use if that's like if those are operations that we need. Okay, so yeah, so again, the overall like structure here is start with the node at the top, the root, right? And continuously keep track of what we need to process next, or what we're currently processing and what we need to process next. When we move on to the next layer, we can take that list that was what we were processing, put it in the nested list, and then start processing the next things to process, right? And just repeat that until we run out of nodes. Okay, so let's tackle the breadth first search solution because I just talked about it for like forever. Let's start with that. Okay, so here's what I'll say is we need, well, we'll say like result is an empty list. Okay, and then we can say if, well, I want to set this up so that we don't need to handle too many edge cases explicitly. We can say if root res.append, oh, not res.append. Okay, we also need, I'll say to process is an empty list, and next to process is also an empty list. Okay, finally, at the top here, we'll say, hey, assuming that there is a root, let's go ahead and put it into the things we need to process. Okay, and then what is our condition? Again, we want to stop when there's nothing left to process. So I'll say while to process. So while there's anything in that list, what do we want to do? Well, we want to go through each node of it, or each thing in that list. So we can say for node in to process. Then what do we want to do? We want to add the children of each node to the next things that we want to process, right? So how do we do that? Well, the other thing here. Okay, let's sorry, one thing at a time. I'm jumping in a million directions, but let's try and get through this like logically. Okay, so for each node that we have to process, what are we going to do? We're going to add its left child and its right child, assuming that there actually is a left and a right child. So I'll say if node.left, then next to process dot append node.left. Okay, and similarly, if node.right, then we'll add to process, we'll add node.right. Okay, now what I was thinking about a second ago, so we put these in, we also are going to want to add, well, so either we'll do this at the beginning or the end. Let me think about this. Yeah, we'll do this at the beginning. We'll say res.append. I think I can do this. So all the nodes that we're about to process, we need to put it into the result, right? Because they're nodes, right? Not only that, but we need to put like a list in. So here's the only thing that I'm concerned about, and we'll see if this becomes an issue, is what we're putting in here is the list that we're currently working with, right? So we need to make sure that we don't like modify that list somewhere else. But yeah, this is what we might call an R value, I believe. So it's like we're putting the current list that we're pointing at into the results list. Okay, so for node into process, if node.left, append, if node.right, append. Okay, and then, yeah, we get all the way through the things that we need to process. And now we can say to process equals next to process. And next to process equals an empty list. Okay, so let's just make sure that we didn't do weird pointer stuff here. This is saying, hey, the thing I was calling to process before, let's make it point at the next things to process, right? And then the next things to process is going to be an empty list. So this doesn't mess with this line. This is totally fine, because when we append to process, we're appending like the current list that we're pointing at. And then over here, we just make it point somewhere else. Okay, so we're going to keep doing this until we run out of things to process, and then when we're done with that, we can just return res. I think that's it. Let's see. I don't know, sometimes weird stuff happens here. Oh, what have I done wrong here? Your output. Oh, wait, am I supposed to put the values? Oh, yeah, sorry, it's a list of ints, my bad. Okay, so what we really want is, okay, so we want to put a list of the values, not the list of nodes itself. So we'll say res.append node.val for node in to process. This is going to produce a new list where for every node in the list, we just grab the value. Great. Okay, and she works. Yippee indeed. Yeah. I wonder, does it give you like the runtime? 0.835. Okay, so, oh, that's really slow. What did I do differently this time? Master, oh, this one used the deck. Yeah, I'm actually kind of surprised that it's that different. Let me just make sure I haven't done anything strange in terms of time complexity here. I think it's just the fact that it's making new lists so often, I think, is the problem. So, you know, in this case, the deck is faster because it's just one data structure that we don't need to reinitialize over and over again. Yeah, you know what? I was going to say maybe we'll try this as a depth first search, but let's actually do this with the deck. I think that's a better use of the time because we've done lots of depth first search. If you have done the, well, here's my hunch because I've never done this as a depth first search or traversal. If you've done the maximum depth of binary tree, that was where we basically like passed along, or the depth first search version of that, we passed along like a counter that would go up and up and up for every level that we went down. As long as we do that as an in-order traversal, so we do the left child and then the self and then the right child, you can use the level to figure out which list you need to add to, right? Because when we're done, it's like a list of lists, right? So you can use the level to say, oh, I know this goes in list 0 or list 2 or whatever it is based on the level that you're at. And as long as you do it as an in-order traversal, you'll end up going through the whole tree left to right. So it'll guarantee that you kind of get things in the correct order rather than like 4, 7, 6, 5. You would get 4, 5, 6, 7. 6, 7. Okay. So definitely doable as a depth first search. It's a little bit more like setup. It's recursion, which is not super fun, but definitely doable. So let's just tweak this to see if we can work with the deck. We're still going to have that result. Instead, we'll just have like a nodes list here. And I can't remember if I have to import. I'm just going to cheat a little bit here. Let me see if I need to import. No, I do not. Okay, great. So deck is built in. Okay, so we are still going to do all of this. We'll say nodes.append the root, and then we'll say while deck. Oh, sorry, while nodes. Okay, and then this is kind of the same actually. We'll append this. And then here's where it differs. We can't do this anymore because we're going to modify the list as we go, and we only want to go through the nodes that we've kind of seen so far. So here's what we'll do instead. We'll say I'll say len nodes equals the length of nodes. And we need this because, again, we're going to like, I'm actually not 100% sure how Python handles this, but the length of that list is going to change as we go. So I don't want to risk having the length built into the loop condition because I don't know if that's going to change. I would probably test it if we had more time, but we don't. So len nodes equals length nodes. And then we'll say for I, and really we don't even need, oh no, actually we do need, we'll say for I in range, len nodes. Okay, so what are we going to do? I believe, I don't actually know what the terminology is. Let's just look this up real quick. I think it's pop front. Pop left, okay, got it. Okay, so we'll say, oh, well, I also need to know if pop left returns the thing. Pretty sure it does. Ugh, this is annoying. Deck pop left Python. You know what? Does deck pop left return the element Python? Yes, it does. Okay, great. Okay, so we'll say next node equals nodes dot pop left. Okay, so this is going to get us the first node that we need to process. And then we can say if next node dot left, then nodes dot append. I think it's append. I really should have done my research on this. Deck append Python. Yeah. I don't know why the, yeah, I thought it was append. I think I kind of prefer like C++'s like terminology is very consistent. Like if it's going to be pop left and push left, why do we not make it pop right and push right? You know what I mean? Anyways, doesn't really matter. So we'll say nodes.append next node.left. If next node.right, nodes.append next node.right. And then, so we've removed the first thing to process. We've added on the new children, if there are any. And then that's it. Eventually, we're going to pop all of the old children. If there are new children, they get added in. And we keep doing that until we run out of things to process. And then we return res. This should still work, I think. So let's find out. Great. And let's see if the time complexity is like massively different. Oh yeah, this is way faster. Memory 13.8 megabytes. Yeah, the list version of this is just like strictly worse, it seems like, unfortunately. So yeah, and then the more you know. I'm actually surprised that it's so extreme. I didn't think that it was, because like we have to make those lists anyways. There's probably something I'm missing as far as like how Python is constructing and keeping track of those lists. Because I am surprised that it's that extreme. Well, anyways, that works. I don't know if we have time to do that. Well, I kind of want to do the depth first version of this because I've never done it before. Yeah, okay, well, let's try this out depth first. So again, I think what we're going to do is we're going to pass along like the current level. Here's, ooh, let me think about this. We're probably going to need a helper function from this. So, and then we need to like pass along the current level that we're at. Okay, which I think should be fine. We'll just create a helper function where You know what? This is so funny. I kind of forgot about this. Whenever I did a depth first search the first time I went through the blind 75, I would call the function penetrate, which I think is so funny. Because that's what it is. You penetrate down into the tree, and then when you run out of things, then you back up and you penetrate again. The tree on the tree, yeah. Okay, so what we're gonna pass is a root and also like the number of the level. Okay, so this is gonna tell us like which list to add to, right? Okay, so we're also gonna need like a results list, and this function is gonna have access to it because it's defined right out here. And then we're gonna call this helper function, and we're gonna pass it the root, and we'll say level 0 at first. Okay. So what penetrate is going to do is it's going to populate the results list, and then so when we're done we can just return res. Okay, so what exactly does this helper function do? It's going to have to... Well, first of all, it's a list of nothing when we start, right? So we're going to need to figure out if we need to append an empty list first. So we can say if level is greater than the length of res minus 1. Yeah. So if we haven't yet created the list that this node belongs to, then we need to append an empty list. Ooh. Okay, wait. We also want a base case. We would say something like if not root, return. Okay. And then if we have not yet created the list, then we can append this. So in this case, by the time we get here, we already know that we have a root. And so we also know at this point that we don't have a list for that root yet. So we can add a list that has the value of the root. Okay, otherwise... Ooh, actually, wait. We need to handle the left subtree first. Again, because we need to go left to right, right? So actually, let me comment this because I'm sort of rambling right now. Process the left subtree. Process the root. And then process the right subtree, right? And so this is going to give us an in-order traversal that'll make us go from left to right. Okay, so this is still fine for the left subtree. We're just going to call this function again. But first we need to figure out if they're actually, well, okay, so the function checks if there's no root. So actually we don't need to do like an if root.left, we'll just let it go to the base case and then fail. So we don't need to say if root.left, we can just say penetrate root.left, and this time the level, since we're going down by 1 child, the level increases by 1, right? Okay, now for the root itself, so once we get to this point and we actually have something to add into result, if we haven't yet created a list for this appropriate level, and we don't know the level ahead of time, right, because we just have to let it kind of run its course, then we create a list. Otherwise, we can say res level dot append root dot val. Ooh, and then this should be right subtree right here, and then this is just do it again on the right subtree. Okay, I don't think we need all this extra space. Okay, and I think that's it. Crazily enough, that was like pretty fast. Oh, hello, welcome in. Aw, that's so sad. Oh, it's not level ordered. I'm so intrigued by that. Oh, no, no, no. Whoa, what's going on here? What? Why did it go to... Slow greater than... I was not expecting that to be the issue, to be honest. If not root return, root dot left. Level plus 1. If the level is greater than len res minus 1, then we append that, which is what I expected. Otherwise, res level dot append root dot val. That's what I expected. Yeah, so this should add it on to the end. And then penetrate root dot right level plus. Well, yeah, I think this is. I'm not seeing any logical errors. What does the tree look like? It's this one over here, so we should obviously get one. Well, it's 1, 2, 3, 4, 5, 6, 7. I have no idea why the 4 went right here. It's the only thing that's wrong. Oh, you know what? I know what the issue is. It's because we went all the way down to this level first, right? So what we actually need to do is we need to continue to add empty lists until we get to like the one that we want, right? So actually what we want here is while level is greater than len res minus 1, we want to res dot append empty list. Great. Okay, so yeah, the issue was, so in terms of depth first search, right, since we're doing this as in order, we're going to go all the way to the left. We're going to keep going left until we cannot go left any further, right? And then at that point, we need to have enough lists to put this in its appropriate level, right? So it's not enough for us to just add on one list. We have to actually add lists at each level. You could also probably do this as like you could do it for each level, but this makes sense to me logically. So yeah, we add on empty lists until we have all the lists that we need, and then once there's enough lists, we can add to the appropriate level. And if this went further at a different place, like if there was another level down here, but we didn't see it till this point, well, that's not a problem because we didn't need that list until we got to that place, right? So we just check, hey, if there's not enough lists, go ahead and make sure that we can make enough lists, right? Or add in enough lists to add to the level we want to add to, and then add to the one that you want to add to. Great. I kind of want to compare the... Yeah, it's pretty slow, unfortunately. It's probably like the recursive, like... Oh, no, this is the deck version. Wait. Am I crazy or did this just change? Yeah, this was the lists version, 52 and 835. Yeah, so this is actually quite comparable to... I just thought, am I crazy or was the deck version not way faster earlier? What happened with that? Yeah, why was this one like incredibly fast? This is the exact same algorithm we used. Anyways, I don't know why the runtime is so weird on this. I don't think that this was a trustworthy... They might have changed like how they check the space or the time complexity. But yeah, so we can do a depth first search. Again, very similar to maximum depth of binary tree, just with some extra fancy stuff to actually like add to a results list for each of these. But again, in order traversal gets us the left to right quality, and then it's pretty standard fare from there. All right, that actually was faster than I thought it was going to be. I had kind of the approach already in my head, so. Great. We'll call it there, and we'll get back to it. Oh, wait, is Monday Veterans Day? No. Wait. Oh, Tuesday is Veterans Day. Okay, so we will be back on Monday. Tuesday. I know, same. I don't have any classes anyways, so it changes nothing for me, but... Oh, no GBM, that's true. Okay, that's okay. We can wait another week. No big. All right, well, have a good night, y'all, and see you Monday.